Hello and welcome to our 20-second session. After we have successfully set up our own local AI workstation by installing Ollama, then open WebUI, we use Docker desktop and installed AnythingLLM, and we are ready to work locally in the pre-production stage. I want to give an introduction of the importance of AI in this pre-production. Before we begin, let us connect this idea to what modern large-scale cinema is demanding today. When audiences talk about film like Dhurandhar and Dhurandhar-2, one thing that keeps coming up is the sheer level of detailing, not just in performance and visuals, but in the way story, screenplay, character design, and production layers feel tightly engineered. Even public coverage around the film has pointed to the scale of its world building, back-to-back production planning, and highly detailed character presentation. What this video explores is a parallel idea, how the same depth of pre-production thinking can now be supported by AI, privately, locally, and with structure. Instead of treating AI as a gimmick, we can use it as a serious pre-production engine, reading long script, isolating scene types, grouping location, organizing shooting logic, and even generating visual planning notes, all offline without risking the intellectual property. If Dhurandhar-level cinema represents peak detailing in story and screenplay execution, this workflow represents how creators can begin building that level of precision earlier at the script breakdown, scheduling, and visual planning stages itself. If you are working on an unreleased screenplay, sending your characters, plot twists, and set pieces to a cloud AI provider, meaning you are giving up control of your intellectual property. No major studio or independent creator can afford that privacy risk. The alternative is running an AI locally on your own machine. But for film production, where documents are hundreds of pages long, standard local models consume system memory rapidly and often crash the workstation. We can solve this hardware limitation by combining Google's new open-weights modern family Gemma 4 with a post-training compression algorithm called TurboQuan. To set this up, you only need three components: a workstation with a modest GPU, a local inference engine like the Ollama, and an interface like AnythingLLM. Integrating these tools gives you enterprise-grade reasoning capabilities, running entirely offline, keeping your script safely on your own hard drive. Step 1 is choosing the right intelligence layer. You need to download the specific open-weight Gemma 4 model that fits your computer's video RAM. This diagram breaks down the hardware requirement at 4-bit quantization. If you are on a consumer laptop with an 8GB GPU, you will pull the E4B variant. If you have the high-end workstation with 32GB of VRAM, you can run the 32 billion parameter model. Getting the model to fit on your graphics card starts the engine. But there is a hidden failure point that hits as soon as you start feeding it the long documents. That failure point is the KV cache. This acts as the model's short-term memory for your current session. Every time you send a message or attach a file, the cache grows, consuming more video RAM until your GPU is completely overwhelmed. We stop this memory explosion by enabling TurboQuan inside your local toolchain. This algorithm physically compresses that conversion history down to roughly 3 bits per value, preserving the model's logic while slashing its footprint. This chart illustrates the exact memory savings. The gray bar shows the high precision memory footprint required by a standard F16 model. With TurboQuan enabled, that requirement drops by a factor of 4. This pushes our context limit from 8,000 to a high capacity 256,000 tokens. To activate this, navigate into the advanced configuration files in your runtime, whether that is Ollama.cpp or VLLM, and explicitly toggle the KV cache compression on. Freeing up that memory upgrades a standard desktop chart interface into a persistent production assistant capable of ingesting high page count documents without freezing. Now that the backend is configured, open your AnythingLLM workspace and prepare your primary pre-production document. Click and drag your full-length 120-page screenplay PDF directly into the active chat window. Watch the system metrics during the file transfer. Because of our compression, video memory consumption remains completely stable, absorbing the script without a dangerous spike. With the memory overhead completely controlled, your GPU has the headroom to dedicate its computing power strictly to deep reasoning. Let's build the prompt. Type a clear instruction telling the AI to read the document and isolate all exterior day scenes. Add your next constraint. Instruct the model to take those isolated scenes and group them based on their specific physical locations. Finally, define the output. Ask it to organize these grouped scenes into a 5-day shooting schedule and deliver the result using structured JSON formatting. This sequence plays directly to Gemma 4's architecture. Google built this model specifically to execute rigid, constraint-based multi-step logic. This system is now conducting a comprehensive scan of all 120 pages simultaneously, cross-referencing which actors are required for which scenes across different acts. It double-checks those character requirements against the time of day continuity, ensuring your lighting constraints match the schedule perfectly. Watch how the raw text of the screenplay physically restructures into actionable logistical data. The logic corrects itself, swapping blocks to optimize travel time between sets. Finally, that completed grid seamlessly translates into perfectly formatted JSON code blocks ready for export. Taking raw creative paragraphs and automatically converting them into structured operational schedules is a core functional strength of an offline AI. We can apply that same logic to visual planning. Gemma 4 is natively multimodal. It processes image and text input in the exact same cognitive step without requiring third-party vision plugins. Drop a raw location scout photo into the chat alongside your scene number and ask the model to generate specific camera blocking and lensing notes. Performing this visual analysis offline protects your unreleased set designs while providing the exact descriptive blueprints you need to feed into local image generators. This chart shows the complete end-to-end workflow. Your raw creative text and reference photos flow directly into the central AI node, separating out into structured logistical calendars and storyboard frames. You executed this complex process completely offline without paying subscription fees or running into out-of-memory errors. Operating natively on local hardware accelerates the speed of your logistical planning, generating technical drafts and schedules in seconds. Your next step is to take your generated storyboard data and feed it directly into a tool like Blender or Unreal Engine to visualize the project. By pairing the complex logic of Gemma 4 with the memory endurance of TurboQuan, you transform a standard personal computer into a persistent private environment for production signing.